textbook, we are working with this book called Life. It is a textbook aimed at first year biology courses. It's co-authored by one of the Stanford faculty members, Craig Heller. It's currently published by Macmillan and is one of the most widely used textbooks for introductory biology courses. So we are creating an intelligent version of this book, and by that what we mean is it's a traditional book which is enhanced by knowledge representation of the content of the book. And once that knowledge representation is available, we use that representation for reasoning, for answering questions, for creating concept summaries, and for suggesting questions as the students read the book. So without telling you more about this, I'm just going to show it to you. So we'll just do a little demo. So as I was saying, this is a book published by Macmillan, written by one of the Stanford faculty members. We currently have first 10 chapters of the book that we have created the representation for, and it's in very well tested form. We have two imagined use cases for students on how they would use it. The first one is reading a book. The second one is doing homework problems by asking questions. So suppose the student is reading about cells, and they are in chapter 6 on cell membranes. And within that chapter, they are in section 6.5, and they are reading. As you can see, many of the words here, they have subtle underlines. And anything that has an underline, one can touch on, and you get a little pop-up definition. As you say more, you get a more detailed page, which superficially looks like a Wikipedia page, but it is actually generated from the knowledge representation. And it's all clickable. You can click on things and get more definitions. We first show the structure of hemoglobin, then we show its functions. And at the bottom, we give further links back into the book. And here you see we are going into section 3.1 and then also in 6.5. This is an example of how we break the linear structure of the book. Reading chapter 6, we should be able to go anywhere else that is more relevant. This graphical representation can also be navigated. And the reason why navigation is so important is it can be driven by students' curiosity. It's kind of like, you go on web and you start surfing the book. So as the student is reading the book, they can highlight any passages. So for example, if they highlight a little section here, the book will automatically compute questions. These questions are again computed based on the knowledge representation and their relevance to the text that they select. These questions serve a variety of purposes. They can serve the purpose of self-test. Have I understood the material? They could also serve the purpose of reminding. If I've forgotten something, I can ask the book and the book will tell you about it. And they could also serve as entry point into further input. So for example, if I touch here on what do hemoglobins carry, the book goes off, it's going off to the server and it's going to compute the answer. And the answer here is hemoglobins carry an oxygen molecule. So for homework problem solving, typically the students would have a set of questions that they have to answer. So we have a question asking dialog where the student can just start typing questions. So I'm going to type a question. As you see, the questions are auto-completed. Okay, so as I pose this question, the answer will be computed, and I'm presented with this very nicely organized table. And regarding the question I was asked, the main differences shown here in the top portion, the main difference between these two processes is one of them begins from extracellular side and ends inside of plasm, and the other one is reverse. Right? And we show both differences as well as similarities. And the interesting thing about this is that we can do this for any two concepts in the knowledge base. It's not like these answers are written by hand, that these can be done only for a small number of questions. as another example, let's ask what is the relationship so this is a relationship question. In response to a question like this, the system will try to compute all possible ways that these two concepts are connected to each other. So here we have shown that endocytosis is related to membrane, in that membrane is a path of endocytosis. And then there is another relationship that endocytosis uses vesicle, which is found in membranes. Right? And there are quite a few other relationships that are displayed. And again, we are driven by the fact that biology is a very qualitative science, and learning biology is about understanding these relationships. As a final example, and in response to a question like this, the system shows me its internal taxonomy, which not only confirms that aquaporin is a protein, but it also tells us what specific kinds of proteins it potentially could be. Okay? So I'm now going to go back to the presentation, unless any of you have any requests or questions.
If he said something, what is the relationship between endocytosis and RNA?
Okay.
I mean, those are really far apart.
It will find it.
It will find it. And in the text, if you highlighted a piece of text here and another piece of text here, how would it do that?
So right now the highlights have to be contiguous.
It's interesting. And what representation of knowledge are you using underneath this?
It's a logic program.
Logic program.
I can get very technical on that if you want.
Well, there's AI programs like Psych that have knowledge representation.
It's a representation system called Knowledge Machine.
Knowledge machine.
Yeah, which was developed at University of Texas at Austin. Okay, so now I'm going to go back to my presentation.
This is something, your version of AI has almost nothing to do with the AI that we've been talking about. Because this is not statistical.
Yeah, this is classical AI.
Right. It's symbolic AI.
It's symbolic.
That's what I used to do, right?
Yeah.
But we lost.
I'm the only hope.
Confidence 101, that's what I mean.
This is old AI.
Classical AI.
Classical.
Classical.
Yeah, classical.
The real AI.
The real AI. Because it's not statistical.
Yeah, it's not statistical. So I think speaking on that, you asked about Psych. So Knowledge Machine was developed by Bruce Porter. He's a former Psych guy.
Yes, yes.
He got frustrated with Psych, he did CAM, and this project is built on that. Okay?
Thank you.
You spoke about, all right. So why is it interesting? Why is it an interesting AI? So most of this technology was developed as part of Project Halo, which was funded by Paul Allen, co-founder of Microsoft. And in that project, we were driven by this goal that we wanted to create a program that will understand a textbook as well as a human does. And so we were trying to get the program to answer questions at the back of the book. So some of the questions that I showed you, there were questions on the back of the book. We can do a lot of questions on the back of the book, but we cannot do all of them. Right? AI is not far enough or sophisticated enough for us to do that. And I should keep going. Yeah, the other thing you could say is that while this answering questions at the back of the book, what's new? This can already be done. We have Watson. Watson did Jeopardy, right? The fact is that the questions at the back of the book, they are not Jeopardy questions, right? The comparison questions, the relationship questions, computing arbitrary connections, that's not Jeopardy. Jeopardy is a single word answer, right? And the main challenge that you have to face in answering questions like this is you have to deal with the intricacies of the natural language in which the concepts are defined. There are, in the biology textbook, you'll find concepts which differ by a single character, right? But they mean completely different things. And this statistical approach completely misses out on them, right? Also, the current AI is not very good at social interactions. And one of the fundamental requirements for social interaction is that even though people are using natural language, they are still able to arrive at an ambiguous understanding of what is being communicated. And the statistical AI is not good at it. It can give you a set of documents and you go figure out which one you want, but it doesn't give you exactly what you're looking for. So somebody asked me this morning, for how long have you been at it? We've been at it for a long time. Right, so we spent quite a few years developing the fundamental technology, the authoring system. We, as I said, we were successful at answering some of the questions, but not all the questions. But our sponsor said, well, you're going to tell me whether it's ever going to be useful. So that was the time when we started looking at how we could put this AI into a book, how we could test in the classrooms. And in a minute, I'll tell you about our results in the classroom. But for the last few years, I've been primarily focused on trying to figure out how we can take this technology and get it out in the real world, in the education settings. So just to give you a little bit of more insight into the way this works, we start from the book, and starting with the book, we create these concept graph type models. And the main challenge in creating these is the choice of the ontology, what semantic relationships we are going to use. And once these models are built, we are able to use them for reasoning and for answering questions. The authoring is done using this system called Aura. So we spent quite a few years trying to get this right. And the main problem we had to address was, how do we bridge between the way the biologist thinks about knowledge and the way computer needs it to be programmed. And inside, this is an example of a complicated, somewhat complicated graph representing mitotic cell cycle. You don't need to read all of this, but the main thing I want to point out here is that there is a lot of representation technology which is hidden in the background, which the domain experts never see, right? And that's where we had to put in a lot of design and creativity to see that what can be put in front of biologists so that they can easily express their knowledge. So why is this interesting for education? Why should we care about this? So biology is a very complex subject. In an introductory course in biology, you have to learn more new words than you would have to learn if you were learning a new language. So so the stuff that we built, we actually tested it in the classroom. And it was not a huge experiment, one day long experiment. And we studied 3 different conditions. This is the AI book, the pure electronic book versus the paper book. And these results show here that the students who were using our AI book, they consistently outperformed the students in the other 2 groups. And if you carefully check the difference between the AI group and the other group was approximately 1 letter grade, which is pretty impressive. So at this point you could ask, okay, what's the problem? Just make it happen and deploy it on a large scale. What are you waiting for, right? So some of and this sort of tries to capture some of the things that we are currently facing and we are addressing. The first and foremost is that the cost of authoring is still pretty high. It takes us a few months to get a chapter into a shape and form that it's precise and sophisticated enough for use by the students. And there are aspects of the AI technology that we need to improve underneath, which will also help us in reducing the cost further. We are in the process saying that, you can use it for reading and homework problem solving. It's certainly the initial level, but people want to go beyond that. And that's where we are starting to experiment with how we can use the capabilities in the book to support critical thinking. And finally, as I showed you, we cover only 10 chapters right now. We are in the process of expanding the coverage to the physiology section of the book. The book I showed you has 55 chapters. Physiology is about 13 chapters. So we are trying to code more chapters so that we can cover more and more of the book. So this is my concluding slide, and these are my main messages that I'd like you to leave with. So first and foremost, simply changing the medium of presentation doesn't do anything for student learning. If you just take a paper and put it into PDF, right, it doesn't do much. And the kind of intelligent textbook that I showed you, I claim it's deeply digital, and deeply digital, and also the initial results show that it improves student learning by as much as one full letter grade. And we also believe that going forward, textbook like this could be a great platform to support critical thinking.